You know, the solid, predictable world you see all around you. That chair you're sitting on, the screen you're looking at. What if I told you it's hiding a deep and frankly bizarre secret? That deep down, at the smallest levels, reality is way stranger and a whole lot more fluid than it seems. Okay, let's dive into this.
Because we're about to explore a pretty revolutionary idea. That matter itself, the very stuff we're all made of, is actually leading a double life. It's an idea that completely flipped our understanding of the universe on its head, suggesting that everything, and I mean everything, from a baseball to an electron, has a hidden, wave-like nature.
Now, to really wrap our heads around how something solid can also be a wave, we got to start with something a little more familiar: light. For centuries, scientists kept running into this puzzle, where light seemed to behave in two totally contradictory ways.
So, on one hand, light acts just like a continuous wave. You see this with things like interference patterns, right? Where light waves pass through little slits and they add up or cancel each other out, making these really distinct patterns. But then, on the other hand, it acts like a stream of tiny individual bullets, particles we call photons. The photoelectric effect is the perfect example. It's not a wave washing over a metal surface, it's a barrage of tiny particles literally knocking electrons loose.
And what's really wild is how close to home this whole duality thing is. Your own eye is the perfect example of this double life in action. The lens of your eye treats light like a wave, bending and focusing it. But the very instant it hits your retina, your rods and cones absorb that light as individual particles, as photons, to create the very sense of vision. Wave and particle, working together just so you can see what's on this screen.
So let's jump to the early 1920s. The duality of light is pretty much established. And along comes this young French physicist, Louis de Broglie. And he asks this deceptively simple, yet totally world-changing question. And it wasn't based on some new experiment, but on this deep, almost philosophical belief in the beauty and balance of nature.
De Broglie kind of looked at the universe and saw two fundamental building blocks. You've got energy, like light, and you've got matter, like us. And he basically reasoned, hey, if nature loves symmetry, and if energy has already been shown to have this dual wave-particle thing going on, then why on earth would matter be any different? For the cosmic scales to be balanced, matter must also have a wave-like side to its personality.
This quote right here, it just gets to the absolute heart of his genius. This wasn't just about crunching numbers. It was about this gut feeling, this intuition that the universe ought to be elegant and consistent. If one half of reality has a dual nature, then the other half must too.
And all of this led to his formal proposal, which we now call the de Broglie hypothesis. He boldly predicted that every single moving object, no matter how big or small, has a wave associated with it. This wasn't just some neat philosophical idea anymore, it was a testable scientific claim. There is a hidden wavelength to everything that moves.
But of course, a hypothesis needs some math to back it up, and de Broglie provided just that. A stunningly elegant and powerful equation that acts like a bridge, connecting the familiar particle world of mass and velocity with this hidden, almost ghostly world of waves.
And this is it, the whole shebang in one simple formula. Lambda equals h over p. Okay, let's break that down. Lambda, that's the Greek letter lambda, stands for the wavelength. That's the wave part. On the other side, p is momentum, which is just mass times velocity. That's the particle part. And the bridge connecting them, that's h, Planck's constant, a fundamental universal number that magically links these two seemingly opposite realities.
So how did he know he wasn't just guessing? Well, he tested it with what we already knew about photons. From Einstein's work, we had a formula for a photon's momentum, p. If you take that formula and just rearrange it to solve for h over p, you're left with c over nu. That's the speed of light, c, divided by the photon's frequency, nu. And here's the beautiful part. In classic wave physics, the speed of a wave divided by its frequency is the very definition of its wavelength, lambda. So because the equation worked perfectly for light, it gave everyone a ton of confidence that it was a universal law that must apply to matter too.
Okay, this brings us to the big question, right? If everything has a wavelength, why don't we see a thrown baseball rippling through the air like a wave in the ocean? Well, the answer lies in the massive difference in scale between our everyday world and the subatomic one. Let's actually run the numbers and see why.
So let's take something totally normal, a ball, weighs about 0.12 kilograms, and it's moving at a pretty brisk 20 meters per second. We can calculate its momentum really easily, just mass times velocity, and that comes out to 2.40 kilogram meters per second.
Now we plug that momentum into de Broglie's equation. We take Planck's constant, divide it by 2.40, and the wavelength we get for this ball is, it's a number so small it's almost meaningless. 2.76 times 10 to the power of negative 34 meters. This number is it's ridiculously tiny. It's many, many, many orders of magnitude smaller than a single proton. It's so small it's completely undetectable and has absolutely zero effect on anything.
Just to put that into perspective, look at this. That is a decimal point followed by 33 zeros before you even get to the first number. So yeah, the wave nature of the ball is technically there, but it is so vanishingly insignificant that for all practical purposes, it might as well not exist. And that's why old-school classical mechanics works perfectly in our big, everyday world.
But now, let's shrink way, way down to the quantum world. Our new subject is a single electron. Its mass is unbelievably tiny, about 9.11 times 10 to the negative 31 kilograms, but it's zipping along really fast, giving it a very small but very real momentum.
When we run this little guy through the exact same de Broglie equation, the result is completely different. The electron's wavelength turns out to be 0.135 nanometers. And as you can see on this chart, that is not a negligible number at all. In fact, it's right in the same ballpark as the wavelength of X-rays. At this tiny scale, the wave nature isn't hidden. It's everything. And this isn't just a fun fact, it's the foundation of incredible tech. Because electrons have such short wavelengths, we can use them in electron microscopes to see things that are way too small for visible light, like viruses or even individual atoms.
So, what have we actually proven here? We've shown that the same universal rule applies to everything, but the consequences of that rule create two totally different realities, and the single deciding factor? It's mass.
It all boils down to this simple inverse relationship. For big, heavy objects with a lot of mass, you get high momentum. And since momentum is on the bottom of that fraction, a big momentum means a tiny, insignificant wavelength. We can totally ignore its wave nature. But for objects with a minuscule mass, like an electron, you get low momentum. And that results in a large, significant wavelength, which makes its wave nature absolutely essential to understanding how it behaves.
So let's just do a quick summary of what we figured out. First, symmetry. Nature treats matter and energy as equals. Both have a dual character. Second, the relation. The equation lambda equals h over p is the universal translator between the particle and wave worlds. Third, the inverse law. The more momentum something has, the smaller its wavelength gets. And finally, the huge role of scale. The wave nature of matter really only shows up and matters in the subatomic world. In our world, it's completely hidden.
Ultimately, what this means is that we live in a dual universe. The solid, predictable reality we all experience every day is really just an illusion created by our massive scale. Our own mass and the mass of everything around us effectively hides our true underlying wave nature. Deep down, at the most fundamental level, matter is never just a particle. It's a beautiful, complex dance of both.
And that leaves us with a final, pretty deep thought. If the very concept of a solid object is just a matter of perspective, if everything is simultaneously a localized little particle and a spread-out wave, then what is reality, really? It's a question that shakes the very foundation of how we see the world, and it all started with a simple, elegant belief in nature's symmetry.